Time for lab 10, a recap lab. All right, so this is a review lab, so it's a little bit different. There's no pre-lab this time. But everybody in your group needs this lab handout. Fill out the top like normal. All right, it's time to work as a team. So what you should have done already is worked with your lab group to complete these questions using your reference tables, calculator, without devices. And now we're gonna go over it. So safety lab review. What does it mean that the goggles are sterilized but not clean? Well, it means that the UV light in the goggle cabinet will kill the germs. It's not washing the goggles. So they may be germ-free but not clean. So remember, we have some alcohol wipes that you can use to clean the lenses if they need to be cleaned. What is the technique you must use for smelling chemicals? Looks like this. Yeah, it's wafting. Wafting. All right, density of water. This is mostly a lab where you learned about measuring and different procedures. So if the volume of a liquid in a graduated cylinder is between the 61 and 62 milliliter lines, what is an appropriate volume to record as the measurement? So possibilities: 61.1, 61.2, 61.3, 0.4, 0.5, 0.6. It has to be 61 point and one digit after the decimal. If you wrote an answer like that, you are correct. All right, now you had to show work here on your paper. The mass of a graduated cylinder filled with mineral oil is 143.29 grams. The volume of the mineral oil was recorded as 84.5 milliliters. The mass of the empty graduated cylinder was 53.01 grams. The accepted value for the density of mineral oil is 0.83 grams per milliliter. What is the mass of the mineral oil? Well, I know the mass of the graduated cylinder filled with mineral oil, and I know the mass of the empty graduated cylinder. So how do I find it? Yeah, I do this subtraction, right? And you should get this as your answer. What is the calculated density? Well, what's the formula for density? Mass over volume, right? So I take the mass that I just calculated divided by the volume that's in the question, and then I do that division in the calculator, and I get this as an answer. Now, what is the percent error? Remember, percent error formula I find on table T, the back of the reference table. What is the measured value? Just figured it out. What's the accepted value in the question? The accepted value is always going to be in the question as the right answer, or I might be able to find it somewhere on the reference table. But for density, that's only elements, and mineral oil is not an element. So now I got to plug it into the right spot. So I do measured minus accepted divided by accepted. Don't forget the times 100. And I get an answer. Okay, and we're going to round to, for percent error, probably one digit after the decimal. You could round to 2 digits after the decimal too. That's okay. Different groups measure the mass of a sample. The values recorded where you can read them there. What is the average mass? So how do I find average? First, add up all the masses. So I do that, I get this number. Now what? Well, I divide by 5. Why? Because I had 5 numbers. I had 5 different masses. So I do the total divided by 5, and that will give me an average. Now, how will I know if my average makes sense? My average should be between the largest number and the smallest number. So the largest number I see is 77.01. It's definitely smaller than that. And it's bigger than 75.12, which is the smallest number. That's how you can tell if your answer is logical. All right, then we did a density extension lab review. So where can density values for elements be located? Hinted at it already. Yeah, that's table S. What is the value we most often use for the density of water? Do you remember? Yeah, it's 1, right? 1 gram per centimeter cubed, or remember, a centimeter cubed is the same as a milliliter, so I could use those interchangeably. Now, how does the density of ice compare to the density of water? The density of ice is less than the density of water. Now, the next part is, how do you know? Well, this, and this. Ice floats, right? If it floats, it must be less dense than water. All right, now let's look at the electrolyte investigation lab review. So define electrolyte. Is a substance that conducts electricity when dissolved in water. What does NaCl with an S mean? That the salt, sodium chloride, is a solid. So then what does NaCl AQ mean? It means that you did what? The salt, sodium chloride, is aqueous, dissolved in water. So it is not just salt, NaCl, it is salt and water. In what state of matter do salts not conduct electricity? Solids. Why? Because their ions cannot move. So the salt would have to be melted or dissolved in water so the ions can move. We need moving charges. Okay, here is just an example of how salts dissolve. You can see the polar water molecules pulling the salt apart, okay? And this is an example of a water molecule, and the oxygen, the red part, is negatively charged. So you can see it gets closer to this potassium, which is positive, okay? And then here you can see for this chlorine right here, these white ones are the hydrogens, and they are positive, the partial positive, so they are closer to the negatives. Okay, so again, in a solid, the ions cannot move, so no conducting electricity, right? So in order to conduct electricity, a salt must be either melted so the charges can move around, or dissolved in water so the charges can move. All right, so how do atoms become cations? They lose electrons. How do atoms become anions? Yeah, they gain electrons, right? The melting points of salts are, let's have a look. Here's a list. What do you think? High. They're solids at room temperature, and they have such strong attractive forces between those positive ions and those negative ions. What do the letters in chemical formulas represent? So here's an example. What do those letters represent? The letters tell the elements in the compound. So here's something to remember. Don't forget this, that when you write an element symbol, the first letter is always capital, and the second letter, for example, in calcium, it would be lowercase, okay? What do the numbers in chemical formulas represent? Well, the numbers tell us what? How many of that atom. So how many of the oxygen atom, or how many of the carbon atom. If there is no number here, that means it's a 1. We just don't write the ones. Why do different salts have different ratios in their chemical formulas? So what do I mean? Why is it MgO, but it's Na3P, and it's Li2S, and it's BaF2? So why are there different ratios? Okay, well, because salts are made of different ions. Ions have different charges because they have different numbers of valence electrons, and the charges have to balance out and be 0. We have to be able to distribute all the electrons so that we fill valence shells. The metals have to get rid of all their electrons, so we end up with different ratios because sodium is a +1 and say, for example, chlorine is a +1, but sodium with a +1 and oxygen with a -2 are going to end up in a different ratio. Think about formulas for salts. Answer each of these with either metal or non-metal. So which one is listed first in a formula? Here's an example. Here's another example. So the metal is first. Which one keeps its name? It doesn't change its name at all. It just keeps whatever it is called on table S. Yeah, that's the metal. Which one has a positive charge? Also the metal. Which one is an anion? That's the nonmetal. Which one is a cation? That's the metal. Ends in IDE, so it doesn't keep its name. It changes. That's the nonmetal. Left side of the periodic table, metal. And which one gains electrons? Non-metal. Okay. All right. The last one that we did, modeling substances. All right, so think about types of bonds. Answer these with either ionic or with covalent. Okay, so here's what happens in ionic. Here's what happens in covalent. Here's another visual and another visual. Okay. When are electrons transferred? Ionic. Metal and a nonmetal? Ionic. Electrons shared? Covalent. Two nonmetals? Covalent. Can be polar? Covalent. Can be nonpolar? Covalent. Which one has stronger, meaning ridiculously strong forces? That's ionic. And which one is found in salts? Ionic. All right, salts always have charges. Is that true or false? Yeah, it's true. Salts always have moving charges. Nope, nope, no, not as a solid, right? Those charges are not moving. All right, so now look at this chart. So we're going to draw a bromine atom. So we're going to look it up on the periodic table and see that bromine has 7 valence electrons. So we're going to draw 7 dots for the bromine atom. For a beryllium atom, we're going to look it up on the periodic table, and its symbol is Be. If you didn't know it, flip to table S, and we can see that it has 2 valence electrons. All right, now we have to do Be, Br2. So I need 1 beryllium and 2 bromines. So I'm going to look where they are in the periodic table. I'm going to see, oh, beryllium is a metal. It's going to give up all of its electrons, and it's going to end up looking like this. One of beryllium's electrons is going to be taken by one of the bromines, and the other one is going to get taken by the other bromine. So you can see the red ones representing what came from beryllium. So this is what you're going to write for this one, remembering that when you have brackets with a positive charge like beryllium, there should be no dots. When you have brackets with a negative charge like the bromide ion, you should have 8 dots. All right, water. We have done this one a whole bunch of times, so you should know what this one looks like. So we start with oxygen and we plug a hydrogen in each of those spots. Why? All of the electrons have to end up being paired. Now, I could draw it like this with lines. Both are acceptable. All right, what about carbon dioxide? So I start with carbon in the middle. I put one of the oxygens here. I put one of the oxygens here. Looks great, except I don't have any more atoms to add, but I still have electrons that aren't paired. So let's restart, and what's going to end up happening is those extra ones are going to move in between, and we're going to end up with some double bonds. Okay. Then next is ammonia. So we do nitrogen and then plug a hydrogen, plug a hydrogen, plug a hydrogen, everything paired up. Okay. All right, so let's do nitrogen. So I start like this. Again, oh man, I don't have any more atoms, but I still have unpaired electrons. So I have to make more bonds, right? So what I'm going to end up having is this 6 electrons being shared between them. All of the electrons end up paired, so it's a triple bond between them. And then the last one on here is methane. You start with carbon and then boom, hydrogen, 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 hydrogen. Oh, it's easy peasy, lemon squeezy, right? All right, think about types of bonds. Answer with polar or nonpolar. So remember, if we're at 0, true nonpolar, but a little baby difference like 0.3, 0.4, nonpolar, or a little baby polar, so tiny little partial charges. As we get closer, like a larger number, it's going to be more polar. And as we cross over about 1.7, we're going to consider it ionic. So for example, the first one, I do that subtraction. The P stands for polar, okay? This one, the N stands for nonpolar. You could call it slightly polar because that's 0.4. So it's a little baby polar, so little baby partial charges. Not super strong ones, but not nothing, okay? Next one, the I stands for ionic. So that's a pretty big difference, okay? And then we continue the process. All right, this one is going to be polar. This one also polar. This one truly nonpolar. The difference is 0. No question about it. Nonpolar. That's it. This one, again, nonpolar, but what do we consider? Little baby polar, right? So there are some slight partial charges, not as much as a lot of the other ones, but not nothing. All right. This one is going to be, again, nonpolar, but little baby polar, right? So slight partial charges. And then lastly, we have ionic, okay? Now, think about types of covalent molecules. Answer with polar or nonpolar. So this has to do with symmetry. So when we have polar molecules, the charge is not balanced. So it's pulling in one direction. There's nothing pulling from the other side. In nonpolar, either there are no partial charges at all. It's a 0 electronegativity difference, right? Or they're pulling in opposite directions. So the charge ends up being balanced or distributed equally. So for water, we should know that it is polar, okay? What about ammonia, which you can see in the picture, is also polar. Carbon dioxide, you can see this in one of the pictures. It is what? Non-polar, because we got oxygen pulling on this side and oxygen pulling on this side. What about H2? Well, that's non-polar. I don't have a polar bond there. Same with O2. Now, what about CH4? That's a little baby polar, like nonpolar, but there's symmetry. So the molecule is nonpolar. That was a lot, but you did it. You made it.